All right, multiplying vectors. There are several ways that we can multiply vectors. So let's start with if we have a vector, let's say f1, and we multiply it by a constant, let's say 3. So we're multiplying it by a scalar. So the idea is we're just adding f1 to itself 3 times. So f1 plus f1 plus f1. So you end up with a vector that has the same direction, but 3 times the length. So this is actually really simple. If f1 was equal to 30 newtons at an angle of 15 degrees, then 3 times f1 will just be 90 newtons at an angle of 15 degrees. Likewise, if f2 was equal to 5 I hat minus 3 j hat newtons, then 3 times f2 would just be equal to 15 I hat minus 9 j hat. We can simply distribute the 3 to the I hat and j hat parts of the vector. So the x component gets 3 times bigger and the y component gets 3 times bigger. So multiplying a vector by a constant is really straightforward and easy. But what if we want to multiply 2 vectors together? So let's say we have a vector, d, and we have a second vector, f, and they have an angle between them of theta. If we want to multiply those together, there are actually 2 different ways to do that multiplication. So the first one is what's called a dot product. So the dot product is written f dot d. And the dot product mathematically is equal to the length of the vector f times the length of the vector d times the cosine of the angle, and this angle is the angle between the f vector and the d vector. So it's not the angle for the f vector, it's not the angle for the d vector, it's the angle between the 2 vectors. Okay, so that's how we do it mathematically. There is another way to calculate this that always works. This is also equal to fx times dx plus fy times dy plus fz times dz. So if you take the x component of the first vector and multiply it by the x component of the second vector, add to that the y component of the first vector times the y component of the second vector, add to that the z component of the third vector plus the z component of the second vector, that will also give you the correct answer for the dot product, which means that these 2 things are also equal to each other, which can be useful for certain problems. Finally, what does the dot product mean mathematically? Well, first of all, the answer that we get here is not a vector, it's a scalar. So this is also sometimes referred to as a scalar So a scalar product or a dot product are the same thing. The reason we call it a dot product is we write it with this dot symbol for multiplication right there. The reason we call it a scalar product is because the answer is a scalar. The answer doesn't have a direction. Graphically, what it means is if you take the first vector and project it onto the second vector, that is, you find out what fraction of the first vector, what portion of the first vector is pointing parallel to the second vector. So we call this the projection of f onto D, the part of f that's parallel to D. Well, that is equal to f cos theta, where f is the length of this vector. And so you can see that f cos theta times D is the dot product. So it's the portion of f that points in the direction of D times D. Okay, so that'll come up in some physics later on in the semester. The next product is called the cross product. So again, we can have two vectors, maybe an r vector and a f vector. And just like before, we need to know the angle between those two vectors. So the cross product, mathematically, the cross product is defined as, so it's written as f cross, well, I'm going to do r cross f r cross f, like that. So that's how we write a cross product. Notice the multiplication symbol here is an x. So with vectors, a dot product and a cross product are two very different things. They have very different meanings. So the cross product, the answer to the cross product is a vector, but it has a length that's equal to the length of the r vector times the length of the second vector, the first vector times the second vector times the sine of the angle between the two vectors. But it also has a direction. So this thing has a direction that I'm going to call n hat, and n is a unit vector that points in a particular direction. Okay, so so this is how we calculate the cross product. It's the length of the r vector times the length of the f vector times the sine of the angle between them, and then the direction that the vector points is something we'll talk about in just a second. There's another way to calculate a cross product, and so r cross f is equal to, and this gets long, so let me try to write it all out. I'm going to try to do this from memory. R y f z minus r z f y in the I hat direction plus r x f, nope, r z f x minus r x f z in the j hat direction plus r x f y minus r y fx in the k-hat direction. And k-hat is the z direction. Just like I hat and j hat are x direction and y direction, k-hat is the z direction. So what is this? This is a crazy formula here. And by the way, this formula includes the direction of the vector as part of the formula because we've got I hat, j hat, and k hat in here. The pattern of this, which is how I can remember it, because believe me, I would not remember this formula if I just had to memorize it. There's a pattern. So if I think of I hat as x and j hat as y and k hat as z, what you can see is this is, in the x direction, we've got y and z, ry and fz, rz and fy. In the y direction, we've got x and z. And in the k direction, we've got x and y. So all three directions are represented, right? Here we've got x, y, and z, and we've got x, y, and z. So all three coordinates are represented. Here this is y, and then z and x, and this is y and x and z. So you see all three different directions are represented in the formula. And then it's just a matter of keeping track of which one is positive and which one is negative. And the order is what matters. X, Y, Z, X, Y, Z. You can see this one goes Y, Z, X. And Y, Z, X is in the forward order, whereas this goes Z, Y, X. And Z, Y, X is in the backwards order, so that's negative. Here, this goes ZXY. ZXY is in the forward order. And here this goes XZY. And XZY is in the backwards order, so it's negative. Here this is XYZ. XYZ is in the positive order, so that's forward. And here this is YXZ. YXZ is in the backwards order, so that's negative. Okay, well, you can also oftentimes look up the formula for cross products. There's also other ways to help remember it, but that's how we calculate a cross product. So, what is a cross product? What does it mean? Well, first of all, geometrically, the idea is we imagine making a parallelogram out of these two vectors by putting another copy of the r vector here and another copy of the f vector here. And then this parallelogram has an area, and the area of that parallelogram is equal to the length of this vector, r times f times sine theta. So mathematically, it tells us the area of that parallelogram, and then the direction is normal to the parallelogram. So remember, normal means 90 degrees pointing away from. So if you want to be normal to this parallelogram, the only two directions that are possible are either out of the page, straight up towards your eyes, or into the page, straight down away from your eyes. So the cross product, the direction, points perpendicular to this parallelogram that's created by the two vectors. Okay, so, but which way? Does it point out of the page or does it point into the page? And to figure that out, we have to use the right-hand rule. And explaining the right-hand rule is not something that's easily done in videos, but we will certainly talk about it a lot in class. Okay, the last thing I wanted to talk about in this video quickly is a unit vector. And a unit vector is any vector that has a length of 1. So these I hat, j hat, and k hat that we've been looking at are called unit vectors. The I hat unit vector is a vector that has a length of 1 and points in the x direction. The j hat unit vector is a vector that has a length of 1 and points in the y direction. And the k hat unit vector is a vector that has a length of 1 and points in the z direction, which in this case would be straight out of the page towards us. But there are other unit vectors. In fact, I can have a unit vector that points in any direction I want as long as it has length 1. Okay, so a lot of times we will want to create a unit vector that points in the same direction as some other vector. So let's say I had a velocity vector that was equal to 3.7 I hat minus 4.2 j hat plus 1.0 k hat meters per second. And I wanted a unit vector that points in the exact same direction. So in order to create a unit vector that points in the same direction, what I'm going to do is I'm going to say, okay, v hat, the unit vector that points in the same direction as v, is going to equal the v vector divided by the length of the v vector. So if this vector had a length of 7 and I divided it by 7, it would have a length of 1. But it would still point in the same direction that the original v vector pointed. So to find the length of a vector, we just use the Pythagorean theorem. So the length of the v vector is equal to the square root of 3.7 squared plus 4.2 squared plus 1.0 squared. So that is equal to 3.7 squared plus, sorry, I'm putting it into my calculator. The square root of all that gives me 5.6859. So my unit vector in the v direction would be equal to 3.7 divided by 5.6859. So that's going to, whoops, I put in my calculator multiplies, I meant divided, 0.6507 I hat minus 4.2 divided by 5.6859, 0.7387 j hat plus 1 divided by 5.6859 gives me 0.1759 k hat. Now this unit vector, because this had units of meters per second, when I divide v by the length of v, the units cancel. So my unit vector has no units, but it should have a length of 1. And to double check that, we can do the square root of 0.6507 squared plus 0.7387 squared plus 0.1759 squared. And let me type that into my calculator, 0.6501 squared plus 0.7787 squared plus 0.1759 squared equals 1.0. All right, so we have created a unit vector which points in the same direction that v points. All right, that is it for this video. I will see you next time.